Welcome! Today we're going to start vector spaces. And so remember that the symbol, the double struck R, is the set of all real numbers. So the numbers that you can fit on the number line. So any number you can pinpoint on here is a real number. Okay, the set double struck C is the set of complex numbers. These are numbers of the form a plus bi, where I is the square root of -1, and a and b are both real numbers. And so you can visualize these as well, where here is the real part, and here is the imaginary part, and then you might have something like a plus bi corresponding to a point in this two-dimensional space, right? But the set of complex numbers, even though we can visualize it like this, it forms what we call a field. Okay, likewise, the set of real numbers form what we call a field. These have algebraic structures with addition and multiplication that make them fields. All right, and so what I'm talking about in brief is addition and multiplication have nice properties, such as there is a neutral element 0 for addition, such that a plus 0 is a, and that's the same as 0 plus a. Likewise, for multiplication, 1 times 7, for example, is equal to 7, which is 7 times 1. And then addition is commutative, addition is associative, multiplication is commutative, multiplication is associative. Every element additively has an additive inverse, it's negative, and every element has a multiplicative inverse, 1 divided by that number. So these are some of the nice properties that I speak of, but we have an appendix to this section or chapter that'll set out all the details of what it means to be a field. And so we'll come back at the end and have a good look at that. So we call this double struck R the set of real numbers because it has an additional algebraic structure to it. With addition and multiplication, we call that the field of scalars when we discuss the real numbers in the context of vector spaces. All right, because there's the set, the real numbers, and then there's the field, the real numbers. So this here you're thinking of as a set, but then if you refer to this, that refers to the field because it's the set of real numbers together with addition and multiplication, and addition and multiplication have nice properties that make them a field. But again, we'll come back to this and have a good look at the definition in our appendix. So likewise, we sometimes refer to the field of complex numbers because again, it has nice properties of addition and multiplication. Okay, so we're going to study vector spaces in this chapter. So consider the following example. And so at first, we'll just look at this from an elementary point of view. Suppose we have the weights of 8 students in kilograms listed as follows. Okay, the weight of student 1, 156 kilograms. Student 2 weighs 125 kilograms, and so on and so on. All right, so these are all the weights of 8 students in kilograms. So we could form a vector out of this, and then in this case it's an 8 tuple because we have 8 coordinates in our representation of this vector W. So W1, W2 up to W8. So the order of the entries is important, right? Because remember, in the third entry, we have 145. that refers to the weight of the third student. Now we can attribute to W a magnitude and a direction, right? But to do that, we need to put this vector in a vector space. And so in this case, the vector space might be the set of all 8 tuples of real numbers. And so the vector space would be this one, R superscript 8. And that's an 8-dimensional vector space. Just as the set of complex numbers over the real numbers is a two-dimensional vector space over the set of real numbers, because we have real numbers possibly going this way and real numbers possibly going this way. So every complex number requires 2 real numbers to describe it. And so the set of complex numbers, which in itself is a field, it is a vector space over the real numbers. And I say over the real numbers because the coordinates are real numbers. Okay, the temperature and speed are scalar quantities. So the temperature of an object and its speed, they're scalar quantities. They have a magnitude only. Force, velocity, momentum, and so on, these are examples of vectors since they have both a magnitude and a direction. Right? For example, I can take my pen and I can push down in a particular direction with a particular quantity of that force. And so since we have both magnitude and direction, we refer to that as a vector. Right? Even this collection of weights, we can attribute a direction to that in an 8-dimensional vector space, and we can take the square root of the sum of the squares, which would give this vector a magnitude. Vectors in 2 space, denoted R superscript 2, for example, 2 minus 5, which you could also write as 2i minus 5j, have 2 components. All right, so 1, 2 components, 1, 2 components. Vectors in 3 space are superscript 3 over the field of real numbers. For example, v is 0, 4, 2, or 4j plus 2k. These have 3 components. And so now we can also consider n space over the real numbers, r superscript n, and they would consist of n tuples. All right, so let's talk now about vector addition. So if we have 2 vectors u and v in n space, r superscript n, so this is an n-dimensional vector space, so n components, and the entries of those are real, or sorry, the components of those vectors are real numbers. All right, so how do we add them? So to add them, we just add their components. All right, let's move on to the next page. So if u and v are vectors in n space, then their sum is defined as u plus v is u1 plus v1, comma, u2 plus v2, and so on up to un plus vn. So in other words, we just add their components, keeping those in order. So to make that, to be able to add them, they have to have the same number of components. So this sum is only defined when the vectors are in the same space. They have to have the same number of components. So for example, I cannot add a vector in a 2-dimensional space to a vector in a 3-dimensional space if those are different vector spaces and the first is not a subset of the other. I have to be able to represent them both in the same dimensional space to be able to add them. Recall that the dot product, or scalar product, another word for it, of u and v is given by u dot v is u1 v1 plus u2 v2 and so on up to un vn. In other words, we just take u and v, we multiply them straight across, and we add the result. Okay, just like this. Now this is shorthand notation for what we have on the left. So this is the sum from I equals 1 to n of ui vi. Now there's another way to write this in terms of matrix multiplication. So if these are both row vectors, then uv transpose, that superscript refers to transpose, this would be, it looks like, we have u1, u2, and so on up to un, and then we're multiplying that by the vector, which you can view as a matrix for the sake of matrix multiplication here. So v1, v2, and so on up to vn. So in other words, I've taken, in transposing, I've taken the row and I've turned that into a column. And now when we take this matrix multiplication, u1 goes with v1, we add that to u2 times v2, and so on up to un times vn. And so we do get this, which is this, and that's just a convenient way to represent the dot product of u and v. Okay, let k be a real number. So this is a scalar, and u be a vector in n space. The scalar multiple k times u is given by ku is ku1, ku2, etc. up to kun. In other words, we take that k and we multiply it by each of the components, and we get out this vector here. All right, let's take a simple example. Minus 2 times the vector 3, minus 8, 1. Okay, we take this minus 2, multiply it by each of the components, and we get minus 6, 16, minus 2. All right, let A and B be m by n matrices. So in other words, m rows and n columns, and these are representatives of that m by n matrix, or matrices. Let P and Q be real numbers. A linear combination of A and B is of the form P times A plus Q times B. In other words, these are scalar multiples of the matrices A and B, but we're viewing those matrices as elements of a vector space. So you're viewing these matrices as vectors, and hence a linear combination takes the scalar P and it multiplies times every element of that matrix. The same for Q, and then adds them together. All right, for example, take, so let's put it over here, e.g. we have a scalar P times a matrix A11, A12, A21, A22 plus Q times B11, B12, B21, B22. Now what does this look like? You see, this is an abbreviated form of this matrix. For example, if you know that M is 2 and N is 2, so that the matrices are 2 by 2, but they could be like 3 by 5, for example. Okay, now let's take this product. So this is this first line. The second line says multiply P times every one of these entries. So we have PA11, PA12, PA21, and PA22. Do the same with this. QB11, QB12, QB21, and QB22. Okay, so that's what this is. This is an abbreviated form of this. And now what's happening in this line is we're just adding the components. keeping those in the same position within those matrices. So this last line refers to PA11 plus QB11 and PA12 plus QB12, PA21 plus QB21, and PA22 plus QB22. Okay, so that's what we have here. This is an abbreviated form of this, when you know that m and n are equal to 2. Okay, now you might have noticed that the subscript here within this matrix refers to the row and column that that entry is in. So for example, take this A21, that's in the second row in the first column, right? Second row, first column. And that's the convention for representing matrices, especially when they're bigger than 2 by 2. Now, if you have a 2 by 2 matrix, it's sometimes natural to call it A, B, C, D, right? But if they get a little bit bigger, say 3 by 3, well, then you very quickly run out of the 26 letters in the alphabet, okay? And so it's more convenient to call them A11, A12, A13, and so on, or in the second row, A21, A22, A23, and so on, just like I've done here. Note that the matrices A and B are elements of a m times n dimensional space. All right, so for example, if m is equal to 2 and n is equal to 2, 2 times 2 is 4, and we have 1, 2, 3, 4 components. So that's what this means, right? Now, equivalently, you could flatten this all out. So let's say, equivalently, the matrix A11, A12, A21, A22, and I'll just put double arrows here to sort of say that I'm thinking of this as another, just the same vector with a different shape. Okay, so in other words, reshape this, and we could say A11, A12, A21, and A22. Right? Okay. So let me just get on the computer here. Type in A subscript I, comma J, some brackets around it. I'm going to show you how easy it is for me to just generate this. Okay, so what I've done here on the computer is I have created a 5 by 7 matrix. You see there are 35 entries in that matrix here on the left. And so I could take this and I could flatten that out. In other words, take each of the rows and then take, I guess, how do I say this? It's not quite a union, is it? Because I don't mean to omit duplicates. I just mean to take out the extra brackets. So here, I'll show you what I mean. I could form from this a 35 tuple. Okay, and it would look like, you see, something like this. Too many entries to represent on a single page, for example. Okay, so let's move down and recall a few definitions about vectors. So let u and v be two vectors in n space, where u is a 1 by n vector. So in other words, a vector with 1 row and n columns. So a row, right? And likewise, v is a row with n entries in it. So 1 row and n columns. Okay, then u and v are orthogonal if their dot product is 0. Okay, let's just find an example of two vectors that are orthogonal. So, e.g., if I choose u to be the vector, just write this as a, well, you know what, I better write it as a row. So 1, 2, 3, for example. Okay, I've written it as a row. I put commas there so that it's clear how these elements are separated. Okay, but you don't have to. You could use a little bit more space and leave out the commas. All right, now if I'm choosing one that's orthogonal, let's see, I might choose the third entry 0, so I have less to consider here. And then between the first and second entry, I'll swap them and put a minus on the second one because I know that the dot product of these will be equal to 0. So u dot v is equal to 1 times 2 plus 2 times minus 1, and this adds up to 0. All right? So we say that u and v are orthogonal when this happens, when their dot product is equal to 0. Okay, so this is a definition of orthogonal. The norm of u is given by the square root of the sum of the squares of the components. So, for example, the norm of this u is the norm of the vector 1, 2, 3, which is the square root of 1 squared plus 2 squared plus 3 squared. 1 squared is 1, 2 squared is 4, and 3 squared is 9. So 1 plus 4 plus 9 is 14. So that vector has norm the square root of 14. Okay, so that's the definition of the norm. Now, here's a property. The norm of u is greater or equal to 0 and equal to 0 if and only if u is equal to the 0 vector. So I'm going to put a tilde under that to remind you it's a vector, not the 0 scalar, but the 0 vector. Okay, so this is one fact. The norm of a vector is greater or equal to 0. And the second fact is the norm of a vector is equal to 0 if and only if it's the 0 vector. All right, so that's what is meant in this third property. Okay, let's move on to our next page. If u is not the 0 vector, then the unit vector u hat is the scalar 1 over the norm of u times the vector u. It's a vector of norm 1, and it has the direction of the vector u. So for an example of this, if I have the vector u, so e.g., if u is equal to the vector, let's go 1, 2, 3 again. We calculated earlier that its norm is the square root of 14. So u hat is a unit vector. This is 1 on root 14 times the vector 1, 2, 3. Right? Now if you take the norm of this, you'll find that the norm of this vector is equal to 1. Okay, so let's try to fit this here in the little space. So the norm of this vector is equal to 1. And sorry, there's not a lot of space between these two, so make your comma really big. Okay, if u and v are not equal to the 0 vector, then the dot product of u and v is the norm of u times the norm of v cos theta, where theta is the angle between u and v. Okay, so suppose we have a u like this, a v there, and an angle theta between u and v. Okay, so you can calculate the angle between u and v by taking the dot product. Remember, on the left, you're taking the product of the components and adding the result. And on the right, you have the norm times cos theta. And so what you can do then is say that cos theta is u dot v over the product of the norms of u and v, and then take the inverse cosine of this, and you get theta, the angle between u and v. But this is only meaningful when the dimension of your vector space is 2 or 3. Okay, so let's note here, only meaningful as an angle when n is 2 or 3. I mean, you can still take this, you can still take the dot product here, that is a scalar or a number, and you can take the product of the norms, that will be a scalar or a number, when n is greater than 3, say, and you can even take the inverse cosine of that number that you get here, right? But then how do you interpret the theta that you get, right? Because if those vectors u and v are in a 4-dimensional space and so have 4 components, how do you visualize the angle between them, right? And so you'd have to take this to mean something more abstract than an angle between the vectors if you have 4 or more dimensions. So if u and v are elements of 3 space, so n equals 3, the dimension of the space equals 3, the cross product, so this is a definition, cross product of u and v is given by u cross v is the determinant, but it's not a real determinant, remember. This is just innate to memory. And the reason why this is not a real determinant is because the entries are not scalars, they are vectors in the top row. Okay, but you can remember what the cross product is by using this as an aid to memory. So determinant of this matrix, okay, and so we expand this in this way, but the I, j, and the k are placeholders, and so we have the vector, cross product is a vector, not a scalar, u2v3 minus u3v2, comma, u3v1 minus u1v3, comma, u1 times u times v2 minus u2 times v1. Okay, that's a vector. It has 3 components here. You see that? So u cross v is orthogonal to both u and v. Okay, so let's draw a little picture of this. So if we have u, and then we have another vector that we place there, v, then our cross product comes out perpendicular to both. Putting a little square there to suggest these angles are 90 degrees, or pi on 2. Okay, the norm of the cross product is equal to the norm of u times the norm of v sine of the angle theta between u and v. So this would be, I guess, a somewhat more calculation intensive version of calculating the angle between u and v. So this would be preferable because it's probably easier to take the dot product than it is to take the cross product. So if u and v are parallel, then the cross product is the 0 vector. Okay, so you do get that nice property of this. Because this is a sine here rather than cos, if you have sine of 0, that's equal to 0, right? So if u and v are parallel vectors, the cross product of u and v is equal to the 0 vector. Okay, we have the following important inequalities for vector norms. And these are very useful when you're proving things about norms. Theorem 17, the Cauchy-Schwartz inequality for any vectors u and v in n space. So they could have n components, where n is, say, any natural number you can think of. the absolute value of u dot v is less than or equal to the product of the norms of u and v. Okay, so let's note here, this is absolute value of the scalar product or dot product u dot v. Theorem 18, the Minkowski or triangle inequality. For any vectors u and v in n space, the norm of u plus v is less than or equal to the sum of the norms of u and v. Now, how do we get the name triangle inequality? Well, draw yourself a triangle on here where the sides are vectors. Okay, so let's put a u for this one, a v for this one, and then let's come across here and write the sum of u and v. Okay, so u plus v. Now what this is saying is that the lengths, the sum of the lengths of these two sides, that is greater than the length of this side of the triangle. All right, so that's why this is called triangle inequality, because you can associate with the side lengths vectors. Now recall that the distance between two vectors is given by the norm of the difference of the two vectors. All right, so I should probably explain this notion a little bit better. Okay, so let's draw a picture down here. So if we have origin here and a point P here and a point Q, say here, all right? Point, remember, I'm talking about points. Okay, origin, P and Q points. Now let's form a vector OP, but let's call it U, lowercase u. Okay, let's form a vector OQ, and let's call that V. Okay, and so now, as points, I can take the difference of the coordinates of these 2 points. All right, so u minus v. What is this as a vector? So u is this. Now minus v would be the arrow going the other way. All right, so we would come out here, I suppose. All right, and let's draw this as u minus v. All right. Now, if I take the norm of u minus v, there's another vector here, right, PQ, which I can obtain by calculating the difference between the points, Q minus P, all right? And so this is parallel to the vector that goes this way, and hence, because the length is the same, this is the same vector. All right, now this over here is the vector PQ. Okay, so this is a distance between these 2 points, but there's a corresponding calculation that says that you can obtain the distance between these 2 points by taking the distance of the 2 vectors. All right, so that's why, and so this is a bit of an abstract notion here, the distance between 2 vectors. All right, let's move on. Now on this page, I'm going to give you some details. So you might want to find a blank piece of paper at this point. Okay, so now let's investigate why the Cauchy-Schwartz inequality should hold true. And remember that says for any vectors u and v in n space, that the absolute value of u dot v, so this is absolute value, is less than or equal to the product of the norms of u and v. So first, if n is equal to 2 or 3, as in 2 or 3 dimensions, then we've got this identity that u dot v is the norm of u times the norm of v cos of the angle theta between u and v. And so now notice that since cos is between -1 and 1, then if we take the absolute value of this line, the absolute value of a norm, since norms are always greater or equal to 0, the absolute value of a norm is just the norm. And then here we have the absolute value of cos theta. Okay, but because of this identity here, the absolute value of cos theta is less than or equal to 1. So this product here on the right is less than or equal to the product of the norms of u and v. Okay, so now let's assume, suppose that the dimension of our vector space n is greater or equal to 4. So if this is the case, then let's let P be the projection of u onto P. So in other words, u dot v over the norm of v squared times v. And we can express this in terms of the unit vector v hat if we just take one of these norms of v and tuck it under the v. So we can write this as u dot v over the norm of v hat, so that v hat has norm 1. Now while we're at it, let's draw a little picture. So remember, this is in 3 space, but it'll be simpler if I just draw this on the page like this without drawing a plane which these vectors are parallel to. So let's just draw it like this so you get the idea. So here I've got u, and then if I project u onto P, it's like I'm shining a torch on the vector, well, as u casts a shadow on P. All right, so this is it's like this, and then while we're at it, let's let Q be perpendicular to P. So Q is u minus P, so that P plus Q add up to u. Okay, and then, so I said projection onto P, but I mean projection onto V, where V is this vector here. So P is parallel, but P is the projection of u onto V. All right, so great. Let's now use Pythagoras' theorem. So by Pythagoras, the sum of the squares of the side lengths of this triangle add up to the square of the side length of the hypotenuse. So in other words, what we have is that the norm of u squared equals the norm of p squared plus the norm of q squared. And here the norm of q, so we've said, well, q is u minus p. So this is the norm of p squared plus the norm of u minus p squared. All right, so now at this point we want to rearrange and solve this equation for the norm of p squared. Just take this over to the other side and then swap sides of the equation. So we'll say it follows that the norm of p squared is equal to the norm of u squared minus the norm of u minus p squared. Okay, and so now what we want to do is make a substitution of what we have up here. We have this expression right here for the vector p. So substituting p equals the norm of u dot norm of v absolute value over the norm of v hat into this expression. So what we need to do then is take the norm of this and square it. So the norm of this vector squared is the norm of this squared. Now norms are multiplicative, so we can break this norm up. This on the numerator is a scalar, this on the denominator is a scalar. So the norm of this vector is the absolute value of this times the norm of this. And we already have absolute value there. We always already have a vector of positive norm in the denominator, since the norm of v is presumably non-zero. So this then is just absolute value of u dot v squared over the norm of v squared, and then multiplied by the norm of v hat squared. But the norm of v hat squared is 1, since the norm of v is 1. So in other words, this is just u dot v absolute value squared over the norm of v squared. And so subbing this into this identity right here, what we have is absolute value of u dot v squared over the norm of v squared is equal to the norm of u squared minus the norm of u minus p squared. Okay, and so at this point what we want to do is multiply throughout by the norm of v squared. So then we have absolute value of u dot v squared equals the norm of u squared times the norm of v squared minus the norm of u minus p squared times the norm of v squared. Now remember, this is a product of two norms right here, but we have a minus sign in front of that. So this is always negative or 0. Okay, and so this entire thing has to be less than or equal to the norm of u squared times the norm of v squared, right? Which is our Cauchy-Schwartz inequality. If you have a look at the top, that's exactly this. So we have given a proof of this identity. Okay, so for this, we want to draw a picture like what we drew earlier. So u, v, and then u plus v. So we start with the calculation u plus v norm squared. Now there's an identity, so what I'm using here is the fact that the square of the norm of w is w dot w. Okay, so applying this identity here, we have u plus v dot u plus v. And now we want to expand this out, keeping in mind that these are vectors. So we have u dot u, then we have plus u dot v, then we have plus v dot u, and then plus v dot v. Okay, now again, due to this identity, u dot u is the norm of u squared. Same for v dot v, but u dot v is equal to v dot u, which is easy enough to demonstrate. So we have 2 of u dot v, and then we have the norm of v squared. Okay, so now remember u dot v, that's a scalar. All right, and so this could be plus or minus, right? The sign of u dot v. And so the greatest that this could be, so something even greater or equal to it, would be the norm of u squared plus twice the absolute value of u dot v plus the norm of v squared. Okay, and now by Cauchy-Schwartz, something even larger than this potentially is the norm of u squared plus 2 times the product of the norms of u and v plus the norm of v squared. Okay, and now looking at this, we can factorize this because these are all scalars now. So we can write this as the sum of the norms, all squared, and then take square roots. Okay, so taking square roots with the knowledge that this is a positive number and the norms are positive numbers, or 0, right? They could be 0, 0, or positive. So we must have the triangle inequality. Okay, great. So let's have a think about a few geometric thinking problems. Find the equation of the plane that passes through the points. Now let's name them. P equals 1, 1, 2, and Q 2, 3, 3, and R 3, minus 3, 3. Okay, now there are a couple of ways to do this if you remember. Since these are points, we might imagine that our plane, so suppose the plane is of the form ax plus by plus cz equals d. In other words, the scalar equation of the plane. And so if these are all points on the plane, then they satisfy this equation. So with x is 1, for example, y is 1, and z is 2. Satisfies the equation. So we get a plus b plus 2c equals d for the first point. For the second point, q, we have 2a plus 3b plus 3c equal to d. And then for the third point, r, we have 3a minus 3b plus 3c equal to d. Okay, now we are going to assume that d is non-zero and see if we get a meaningful result by doing that. Okay, so we'll say if d is not equal to 0, then we can divide by d and let uppercase a be lowercase a over lowercase d, uppercase b be lowercase b over lowercase d, and uppercase c be lowercase c over lowercase d. I'm going to draw a vertical line here because we'll take another approach also. And so rewriting these equations, having divided throughout by lowercase d, we would have uppercase a plus uppercase b plus uppercase, or 2 uppercase c equal to 1. And then 2a plus 3b plus 3c equal to 1. 3a minus 3b plus 3c equals 1. And then we could solve this as a system of linear equations and get a is minus 2 over 3, b is minus 1 over 9, and c is 8 over 9. And since we did get meaningful numbers here, it says yes, we didn't get any contradiction with the assumption that d is 0, so this is fine. And so that gives us the scalar equation of the plane that these 3 points pass through. Okay, and just by subbing these in up here. All right, now there's another approach. So in this approach, let's draw a little picture here. So suppose we have a plane and we're seeking the equation of this plane. All right, let's suppose that n is a normal vector to the plane, so perpendicular to the plane. And so I want to take, let's see, the vector r from the point P, which is a point on the plane, right? And P is this point, to the vector x, or sorry, to the point x. But we can also think of it as a vector if we have the origin here. There's the origin to the vector, or to the point, makes the vector OX. And the vector from O to P, to the point P, makes the vector OP. But the point X is lowercase x, lowercase y, and lowercase z. Okay, so let's call the vector from the point P to the point X, let's call that R, and consider what R is. So R equals Px, the vector from the point P to the vector, sorry, the point P to the vector to the point X. Okay. This is X minus P, difference of points. Can think of it as a difference of points because the vector x is the vector from O to x, and so it has the same coordinates as the vector x. All right, and so this is lowercase x, y, z, minus p is 1, 1, 2. And so r is the vector x minus 1, y minus 1, z minus 2. Okay, now the normal vector is perpendicular to r because r lies parallel to the plane containing the 3 points. Okay, so R dot n is the zero vector, or sorry, the zero scalar, right? Since R and n are perpendicular or orthogonal. Okay, now we can get n by taking a cross product of PQ. Right, so here you might draw Q, for example, and then here you might draw the point R, uppercase R. Okay, so taking these vectors and crossing those, a vector perpendicular to both would be n. So n is equal to PQ cross PR, and so that is the cross product of the vectors 1, 2, 1. Remember, I get this by taking Q minus P. So Q minus P, 3 minus 2 is 1. For example, 2 minus 1 is 1, 3 minus 1 is 2, so 1, 2, 1. Okay, cross PR. Again, PR is R minus P. So I've got 2 minus 4, 1. And then I set up that cross product. In aid to memory, you can do this as the determinant of a 3 by 3 matrix with the unit vectors ijk in the top row. And then you place this in the second row and this in the third row. Okay, and that cross product gives us a vector. It's the vector 6 minus 6 plus 1 minus 8. Okay, so we have n. This is n. And we have r. This is r. So taking the dot product of n and r, so n dot r should be equal to 0. But that cross product is, dot product is 6 times x minus 1. So 6x minus 6 plus 1 times y minus 1. So plus y minus 1. And then plus minus 8 times z minus 2. So minus 8z plus 16. And this, because the dot product here is 0, this is equal to 0. So this gives us a scalar equation of the plane. It gives us 6x plus y minus 8z is minus 9. Okay, and if you look carefully at this will be the same thing as we got via this other method, or it should be. Yes, it'll give us the same as we got via this. Okay, example 8.3. Find the distance from the point 2, 0, 0 to the plane x plus 2y plus 2z equals 0. So let's draw a picture. So here we have a plane. And then let's suppose that this is our normal vector. And then we have this point 2, 0, 0. And then let's suppose that in line, so that these connect with a line. So in other words, you're moving your normal vector so that it passes through this point right here. And then there's another one where that line intersects. Let's call it P for now. Intersects the plane. Okay, so now let's parameterize the line passing through these two via the vector equation. So r equals, now we know what the normal is, right? Because we can just read it off of the coefficients here. So the normal vector n is the vector 1, 2, 2. Okay, just from reading from the coefficients here. So we can take this as a direction vector because that normal vector is parallel to the line passing through this point 2, 0, 0 and another point that is on the plane. And the distance is the least distance, or the distance between this point P and this point 2, 0, 0. So we really need to find the coordinates of the point P. But to do so, we first need to parameterize this line going through both of them. Okay, and so it's parallel to the normal vector 1, 2, 2. So 1, 2, 2 times a scalar lambda plus 2, 0, 0, because that is on our line as a point. Okay, but we need to view it here as a vector, as in, you know, from the vector O to the point so we have a vector, right? Okay, so that is 2, 0, 0 there. Now this describes a collection of vectors that are parallel to n, but it also describes a collection of points on this line by you choosing any real parameter lambda. Okay, so for example, if we chose lambda equals 0, then we would get this point. All right, so next what you need to do is find where this intersects with the plane. Okay, and so from this we get a description of points. So expanding this out, we have lambda plus 2, then we have 2 lambda and 2 lambda. All right, so we can get a point by expanding this out because it also describes points. Okay, and now subbing this into this equation, we've got lambda plus 2 plus 2 times 2 lambda plus 2 times 2 lambda equals 0, which gives us a way to solve for lambda. All right, so if we expand this out, we get 5 lambda equals minus 2, and then divide both sides by 5, and we get lambda is minus 2/5. Okay, so from that, oh no, that's a 9, isn't it? Yeah, so minus 2/9. There we go. And so from that, we can use this to find the point. Okay, so P is then 2 minus 2 over 9, which is 16 over 9. And this coordinate is minus 4 over 9. And this coordinate is minus 4 over 9. And then we just take the distance between this point P and this point right here, and we get the distance between the point and the plane.